Okay, so you can get access to rows by asking for a component here. So for instance, we can ask R0, and this is going to be the first row, R1 the second, etc. And one way to do it, to create this list dynamically, is to say, for instance, allocate a list like I did before for an output. This is actually what you should not do, but let's do it. And then you say, for instance, for I in range len of R, you can access it this way, or you can say R dot shape 0. So this is the size of the this is the number of rows. So if I say R dot shape, I get the array is shape 10, 9. And if I take 0, I get 10, right? So I can say for I in range array shape 0, I say out dot append R of I. So basically we are appending in the output rows of the matrix, and now our output is a list of rows. Okay, this is what you should aim to. This could be your function, but there is a much easier way to do it by actually automatically creating a list. And if you say you list the array, Python is already doing the job for you and is listing the component of the array and just actually returning the same output. This is because array is iterable. So if, for instance, I say, when I do a for loop on the array, I say for row in R, basically I name it row because actually I'm going through the rows, okay? And so the array is iterable, so these are the rows, I can access the rows, and so I can just list it and get the same output, right? So the solution to the first one is to basically do list, to return list of R. And what is the solution of the second one? There was an hint in the text that you may want to use the transpose, because if you do array.t, you're actually transposing the array. We saw this doesn't create a copy of the array, it's for free the transpose, it's the same data. So it's a good operation to do, and it's not bad, and it's going to basically change the order of the matrix, and what were row become column, and what were column become row. So basically the second one can be easy, say, get rows of R dot t. So this is, I'm actually using the same function I created before and just transposing the matrix. Okay, so this was the solution to the first one. Okay. Any question? Then there was an extra exercise.
Simone, so you does it so for a row in array, so doesn't I mean wouldn't it go through the elements of the array?
No, we'll go through the first axis. So when you try to iterate an array, the array is a given shape, right? And so when you try to iterate it, you will go through the outer index. So this is a matrix, and if you try to go through the elements of the array, the elements of the array are actually rows under this point of view. And then if you iterate the rows, you get the single values. Okay, but it's jumping from a row to another when you try to iterate it in this way. And basically, each row is just a view of the same array. So I'm not allocating memory here. Each of these, if I ask, if I take a component, they're actually still pointing to the same array, like I said before. So if I take the second and I say array interface, this is actually a slice. And so this guy is pointing to the same, but doing by switching by point, but starting from another point. Okay. Now, there was an extra year for getting row vectors. So basically, the requirement now is to don't lose the fact that it's a matrix. And so if you want to get rows, here I was asking to get the rows as a shape 1m. So the matrix is m times m. You want to get the shape as 1m and the other n1. Okay. How do we do this? Well, we do something similar, but what do we need to do? So now we want to have, let's start from the first. We want to get something that has shape 1m. So our array now has shape nm are 10 and 9. If I want to get list of rows, I mean, if I want to get rows that are that have the shape 1m, well, basically I could list it and reshape all of them. Or the other way around is to say, to change the shape of the array. So if I say colon comma none, right? If I say colon comma none, I added for free a new axis here. You see where I'm going? So if I say none, I'm adding for free a new axis. This is still the same array. And the number of elements of the array is the product of the components. So I can for free add as many axes as I want without having to create a new array, because these are still the same number of data, right? So if I say colon comma none, now it's shape 10, 1, 9. And if I list it, right? If I list it, now I get rows or vectors of rows. You see, there are double parentheses. It's different from the previous because now there is a shape 1, 9 and not 9, 1. So this is just an exercise that you can do. Try to do by your own how to do the column vector. So you can use a similar way to do it in one line. So we not do it now, but you can try later to do column vector by your own. Okay. Any question? Anyone that feels brave and want to tell me the solution of this out of art? No? So I'll let you think about it. We go further. Okay. Now, another important topic that I would like to cover is about what we already mentioned before, are the vectorized functions. So far, there should be this message, should be clear this message that Python, NumPy is doing everything in a vectorized way, and it's basically just looping with compiled code the functions, the array, sorry. And for this, it provides you a large number of functions that are named universal functions, and these are basically element-wise operations. So they are acting on each element. Like we did now, the sum of two arrays, for instance, those go element-wise and they sum two arrays. If you ask the square root, it's going to do the square root of every number inside the array. The same is true for the exponential, the cosinus. So these are named unary functions because they take only one argument. Binary functions take two arguments. And then we have reductions. So reductions are functions that reduce the size. Basically, you go from a matrix to something that has less dimensions. Okay. Okay, here I think, okay, I think it's quite understandable. So if I create, for instance, an array of 1, then I'm adding 2. So this is an array of 3s in this case. Then I'm adding 3 to 1 because I'm adding the two arrays together. I take the square root, I get 2. So basically, this is just a set of operations that are acting element-wise, and you're getting the same result. Okay. And if I say sum, I can just ask to sum everything and obtain this. in the same way, like you sum, you can ask for the product, the mean, and you can, it's plenty of function to use, and these are very user-friendly and understandable. So I would have also a slide on that. This is about item accessing, so you have it there. And these are universal functions. Okay. I think this should be fine. Before going here, let's talk about an issue of NumPy though, on this point of view. So NumPy is faster. It does all these operations in a vectorized format and very fast. But when you use NumPy, you can never really reach C performance. And the reason is this one. What is, for instance, the difference between the left and right? So both of them are doing the same calculation. They are doing x squared plus 2x plus 1. This is done with NumPy over the word, right? The right-hand side is a for loop that goes over the elements and does assign the value of y of the x squared plus 2x plus 1. But what is the difference between the two approaches? Sorry? No. They have the same number of floating point operations. That is the same because you do still the same calculations. Okay. What is the major issue that it's differentiating the two ways of doing this? The point is that in a for loop, this set of operations are done per element. So you are directly doing this operation and assigning it. The other one does the operation per literally as it's written. So first it does x to the power 2, then it does 2 times x, then it sums them together, and then it sums 1. So the difference on this left-hand side, that is a performance drawback of this way of doing calculations, is that the NumPy itself, it doesn't know really what you want to do. So NumPy will be asked to do an operation per time. So first it will be asked, okay, do me x squared. Okay, I do it, and I give you. Then you know that this operation needs to go in order, so I do first multiplication, I do 2 times x. Okay, I do it, and I give you another array. So NumPy is creating an intermediate 2 temporary array where it stops this operation. And then Python is asking, okay, now that you got these two results, do an addition. I sum them, I get a3. And then here that I'm a3, I sum 1, I get y. So doing this in Python is required to do 4 for loops because I have to do 1, 2, 3, 4 for loops on the data. I had to do 5 array access because I had to access x here, A1, A2, A3 in order to do it. So I accessed 5 different array in memory. And I had to create 3 extra arrays in memory. So these created more space in memory for getting y. Of course, all of this is trashed away, but for arriving here, I had to create these temporary arrays. On the right-hand side, nothing. C does simply access the array once. You get x1 here, x1 here. The compiler will optimize it for you. Just gets it once, does multiplication, stores them, and you have the result. You don't have any extra memory allocated. You have only one array access, only one for loop. And this is something that you can never achieve with NumPy. Okay? In NumPy, we will always be pedantic in doing all these operations. And this is something that costs more than what C will do. So you will never get exactly the C performance unless you do some tricks like we are going to see with NumPy. But this is an issue of these vectorized operation that go loop per loop. The same issue, for instance, you have it with C++ with any object-oriented language, unless you're very careful. So it's still very fast, but it's a performance drawback. So it's not as fast as C. It can be maybe 10% slower, 20% slower. It's are small numbers, but there is a difference. Okay. Any question on this? So you need to be careful that any operation that you do counts in on NumPy side. Okay. So if there are no questions, I will go comment another very nice feature of NumPy that is about the axis. So another very interesting feature of NumPy that allows you to increase the workload is to use this multidimensionality of your system to basically do many operations in parallel and then reduce them up to a point that is required. So suppose you have multiple set, an array like this, let's say an array of shape 10, 100, I could interpret it, well, I shouldn't print it, sorry. I could interpret it as 10 times 100 measurements of my experiment, right? So you can interpret the first index as the multiplicity of your experiment, of your data set, and then this is actually the data size. The same can come true for many other things. For instance, you have an image you can store it. For instance, you can store it with something that has a shape, the number of images. Then you can have the X and Y that are the size of the image, right? Then you can have, for instance, 3 that are the RGB values. And you can have many other components and see this as a multidimensional array. So this allows you to put inside one unique array a lot of data. As far as the sizes of each column is the same. So you have all images, a requirement is that all images have the same size X and Y. If they are different size, you could then actually do this. So you can put everything together and then you can nicely do operation axis-wise. So if I'm here now, I created these 100 elements. Something very interesting is that now I can store this in an array, okay? And this now is this array with shape 10, 100. And for instance, I can ask, okay, I can say array.sum, and this will give me the sum of everything. But this is maybe not the most interesting thing you want to do, because if these are 10 experiments, maybe you want to do the sum over the 100. So here you can say axis equal 1, and this will return you 10 numbers where the operation, the sum is done along the axis 100. And the same you can do in the opposite way and say axis 0, and so do the sum along the 0 axis and get 100 numbers as output. So this is a nice feature that the axis allows you to, and here it's a bit more explained, you can read more about it. And basically, you can. It's very powerful to be able to do things axis-wise because allows you to make the arrays much bigger and then be able to do operations along certain axes. Okay, here there will be another exercise. Just maybe I think there are more interesting things to have a look at. So I will let you do it maybe later if we have some time. Let's see how it goes now. So basically this exercise is about getting a set of matrices that is size n and m, and you want to compute the angle between different vectors. So you consider this matrix not actually as a matrix, but to be n vectors of size m. And you want to compute this quantity. So you would like to write this function that computes the norms x square, y square, and x and y, like written here. So this it's an exercise that you could try doing and complete it here. If there are no questions about this part, axis and universal function, we'll move to another nice feature that is broadcasting. Any question here? Okay, online? Okay. Then let's see two more things. One is broadcasting and then NumPy. And then I think we can have some discussion. So broadcasting. Broadcasting is another very, very nice feature of NumPy that maybe it's easier to explain with some slides. And basically, another cool thing that NumPy does is to allow you to do operations between arrays that do not have the same size. And this it's very useful for various reasons, and I'm going to explain some of them. But let's first understand how this works. So we said these operations that we said so far are element-wise operations. So you can only do them if the arrays have exactly the same size, and then these get matched component by component, and component by component, the operation is done, and you get the result, right? So you're going over each axis. Broadcasting, though, is something that allows you to actually save memory and make your code much faster by avoiding to repeat components in your array, but actually letting NumPy to reduce how these operations should be done. So for instance, you see here we have 0, 1, 2 repeated 4 times because we want to sum basically these 4 numbers with these 3 numbers and get all the combination here. A way to make it faster the code and save memory is to basically just say 0, 1, 2 with a shape 1, 3. And if I add it to something that has shape 4, 3, automatically NumPy will consider this as the one as an axis that can be extended, and it will add 0, 1, 2 to every row of this matrix that is size 4, 3. Okay, so this it allows you, this is then broadcasting because it's basically broadcasting the same information overall. Okay, the same is true in the opposite way. So I do for 1 because indeed here I have the same information for every column. I used to do for 1, and so NumPy can match the 1 and say, since this is 3, the output should have size 4, 1 and 1, 3. So I combine them, and this becomes 4 times 3, and I do the same operation for every column and every row. Okay, so this is very, very, very nice and very useful. And the rule is that NumPy match the size from right to left. So here I could actually have something of size 3. They don't have to have the same shape, but you can have something of size 3 and will be matched right to left. Okay, just piece of information.
What about multiplication? Because that can be ambiguous.
Yeah, no, it's the same. It's the same because it's not a matrix. Multiplication in NumPy doesn't mean matrix vector multiplication. Multiplication is always element-wise. So what is happening for plus, it's happening for the multiplication. So multiplication, it's not the dot product. It's something else. I think that's why you mean it is ambiguous, right? Or how is it ambiguous, the multiplication?
Yes, for example, in the last example, in the last line, if you had the reverse order and you have multiplication,
what is the reverse order?
If you had 1,3 multiplying 4,1.
Okay, but it's also, the multiplication is also commuting, but let's say a difference. Of course, but it's doing the operation like this always. It's just filling up the matrix. The sign, what is in the middle doesn't matter. It's always a binary operation. Okay, there is no ambiguity. It's always keeping the order and filling up. We are going to see examples now. Okay. So basically, broadcasting is something very naive, but also very powerful. So it's something like what we did before. For instance, we are doing R1 plus 2. Doing this operation, this is actually already broadcasting because doing plus 2, for you it's intuitive. It's just adding 2 to the array, but it's kind of broadcasting. It's adding 2 to all components. It's one number, it's going to add it to all components, right? But in the same way, now I can define, for instance, this array as zeros. And what is going to happen now if I add this matrix of 0 with the array of shape 0, 1, 2? So if I do this operation, what do you expect? Zero, 1, 2 again for every row, exactly. Because it's doing it operation-wise, okay? And if I wanted to do the opposite, I wanted to have 0, 1, 2, but per column now. What do you need to do? So you see the shape. The shape of R1 and R2 is so the shape of R1, R2 are R2 is 3 by 3, R1 is 3, and I told you this is matched right to left. So because indeed you see that it's intuitive, I'm adding these components for every row. If I want to add them for every column, what do I need to do? I need to reshape this one to make it of a shape 1, 3, 1. Okay, like I'm doing here. So I can use none to increase the shape. Now array 3 is a shape 3, 1. So it's something that looks like this. It's a column now. And of course, it's again very intuitive. If I'm adding this column to this matrix, what you get? You get 3 columns that have the same elements. And this is very useful because if you want to scale some number element-wise, it's very faster to do it much faster to do it in this way, and it's a very good feature. So if you want to, for instance, let's go back to the example I made you before. We have an image of this kind. I want to scale all the colors. Well, I just multiply by three value, and this applies to all of them. I want to scale in some way the value per position along certain axes. I just put values along certain axes, and this is going to change axis-wise the content of this array. Okay. Yeah.
I'm just thinking about there's this array that we just reshape. Suppose we transport the array without doing the reshape. Is it going to give the same result?
Good question. No, because it doesn't know. It would if the shape that you give it's different. Let me explain better. So R1, we say a shape 3. So if I transpose R1, the transposition of this still gives me something that has shape 3. It doesn't add automatically a 1 because for NumPy these are not matrices. So this at the moment it's still an array, and so reshaping, changing the order of axis gives you the same thing. To transpose something the same way, I need to make it first an array of vectors like we did before in the exercise. So if I add none now the none is shape 3, 1, which is still the same. I just say now it's a vector. It's a vector row. So this now is the shape is 3, 1. Sorry, 1, 3, 1, 3, because I don't know at the beginning. And if now I do T, now it's changing the order and it's 3, 1. So this way it does the same, but you need to first have the correct shape. Okay. Okay. Other questions? Okay, so now let's do, you know that at school you learn the product table. So I want to learn what is the product of one number. So let's say I have a range. I have a range that goes 111. So this is something that has these some numbers that are like these, okay? And I want to do the product table of 1 times every other number up to 10. So I want to build up the cross product table between 1 to 10. This thing is something you can do very easily now with NumPy. What should I do? Basically, I have this X right? And what do I need to multiply by? So I want to do every cross number. So if I do x times x, what do I get? Well, I get the product of itself. I just get one. These are powers. It's not really what I want to do. If now I do, for instance, x column none, like this, now I get the first one is the row, the second one is the column, and basically now doing x times x none, it did every cross product. Do you see it? Because x column none is a vector now. So if I do this, the product of this one times this one, I get this matrix. Right? So this is, for instance, something very easy that you can achieve. And I don't know how many of you needs to build up covariance matrix, for instance, but if you want to build a covariance matrix, so basically the covariance between one element and the other, who knows what is a covariance matrix? Okay, how do you do a covariance matrix here now? So if I need to do a covariance matrix between, basically the covariance matrix is something that is defined, I do x minus x min, okay, this would be the standard deviation, and I need to multiply it by the x minus x min for any other component. So I want to, the covariance is defined between the covariance of x comma y is defined as the x minus x min, let's name it par x, times y minus y min, right? So I want to do the, I want to build up this covariance matrix. How do I do it? Any idea? The answer is the same, it's here. I want to do every cross product of every component. So this is how I do x minus x min, right? If I want to do every cross product, how do I do it? Well, I store this in y, right? And then I want to do y, the same with here. This is going to give me the cross product between y and itself and any other component. So this is going to be a covariance matrix.
Sorry, just to make sure I get what this nonlinear does, it just adds an extra dimension.
The non, yes, it's just add an extra dimension. So basically makes what was a row a column. It's very useful instead of reshaping. You achieve the same goal as saying dot reshape, but then you need to need the size, or you need to know the size, or if I say, because here would be 10,1, this would be the same goal, the same result, but you need to know the size, or you want to use a -1, but you need to call reshape. Instead, I can just say colon none, and I'm adding an additional dimension that is this one.
Okay, thank you.
Yeah. Okay. Okay. So this is very powerful because I did automatically without creating a matrix of the cross product. Right? You understand? Any question? Okay. So broadcasting, it's a very key feature also of NumPy that I don't think many other languages do. Or better, it was introduced here and then many other places being used as well. Okay, so far I have stressed a lot the fact that you should always use NumPy for doing this kind of operation. And this becomes very easy as far as you need to do element-wise operation. Okay, But what if your problem is more complicated? So I don't know, you need to do, you have machine learning and you need to do a convolution, or you just need to do some other different operation like the difference between two neighboring components. So for instance, you want to compute numerically a derivative. How do you compute numerically a derivative of a function? How do you compute numerical derivative of function? So let's say I want to do some function. Let's say I have an mp.linspace between, this is going to create a continuous space between 0 and let's say 2 times mp.py. This is my x. Right, so this is a continuous space, and on this x I compute y as the sine of x. Okay, this is what, sorry, mp.sine. Now, if I want to plot it, what do I do? I can use, where before we see with pandas, you can say import, you can say from matplotlib import by plot as plt, and then you can say plt.plot x comma y. And here basically we have a sine, okay? I want to compute its derivative. How do I do it numerically? What is the definition of derivative? Finite difference, perfect. So you want to do the difference of one component and the next, and that's your delta H, and compute it and compute the derivative, right? How do you do this with NumPy? So how can I do it with NumPy? Basically, I have y, right? Y are my values, and I need to basically do the difference between this and the next one. How can I do it with NumPy? I cannot do y minus y because this is 0 and not shifting it. I mean, that's the key. You need to shift them. So how can I say NumPy that I want to do an operation on a shift? Anybody knows? I told you it's very good in element-wise, but these are things that you need always to, you need to kind of find a way how to do it, okay? I believe you can do anything with NumPy, just you need to learn more about the tools that gives you to do that. So for instance, I want to do the difference between one and the next. Basically, I would like to do the difference between the component 1 and the component 0. Right? This is what I would like to do. And repeat it for every I. Of course, one way is to do it with a for loop, but as I already told, it's a no-go. But let's do it. Let's do it as a for loop. How will you do it? So you can say n is the size of the array. Out is going to be 0 like the array, just to create an empty output. And then I assign to every component of the output the diff y plus 1 minus y of I. Okay. So here I'm doing a for loop and I'm assigning 1 plus 1 minus y of I. Why do I have the percentage n? What does it mean, this? I like the faces. So the percentage n, it's a module because if I arrive at the end of the array, so these are 50 elements, I can go up to 49, right? I can ask what is the element of 49. But if I ask the value of 50, what do I get? I get an error. Will tell me there is no element number 50. But in order to do the difference for all values, either I iterate up to n minus 1, that's possible, or I just want to start from the beginning and 50 to be equal 0. If I do percentage n is the size, so 50 percentage 50 does 0. The percentage operation is named module. So this tells me the the module operation is how much is left out of the number. So 49 percentage 50 is 49. And this is true from 0 to 50 to 49, and then we start back again. This is a module. Your module. So this is how you will do it. And then this is my output. And then I plot it. I say, PLT plot X come out. And now what do we get? We got a cosine. So this was a sine. Now we got a cosine. Okay, ignore the last one because, okay, we are going to the boundary. Okay, any question here? So we had to use Python. Is this a good way? This is what I try to tell you not to do, and I'm ending up in doing it. So this is not the correct way. I told you NumPy gives you all the tools for doing this. What is the tool that NumPy gives you to do the operation between two arrays? Well, this is named, for instance, roll. So now I have my Y, or sorry, let's start, let's name now R. So we have 10 numbers. The function that NumPy gives you is the roll function. Roll is going to do what it says. It's going to roll every element backward or forward of a number. So if I roll the array of -1, now everything got rolled backwards, and I got the 0 there, and everything came back here. If I do +1, I can do it. I can do it forward. I had a multidimensional matrix, so let's do this reshape as 5,2. So for instance, I want to do it as along certain axis. I can simply say R roll of 1, comma, axis equals 0. And now all the array is rolled along axis 0, like this. So you see that axis is very powerful. We are rolling only according to certain axes. And for instance, this is a very another important NumPy operation that you should know. It allows you to move things around. And let's go back now to our problem. We want to do the difference, the final difference between two elements. So what do we need to do?
Sorry, I missed. Does the roll operation give you the same size, or it?
Yeah, it's the same size. It uses a kind of periodic boundary condition. So
Okay, yes. Okay.
Yeah. So what do we need to do for doing the final difference? We want to do this operation. So what do we need to do? Yeah. Exactly. You need to roll the first one and subtract the non-rolled version of it. This is how to do the final difference. So you do np.roll r minus r1. This is the difference. And if now I give, let's call it again of y, now it's going to do the same as I did before. And if I plot it, I keep obtaining the same. Okay. Any question here? So NumPy gives you.
Wasn't it the roll of +1?
And it's -1 actually in this case, because you want, it's always confusing also for me, but if I say, we had it before this example, now I want to shift it. It's always good to try it first the roll and see that it does what you want. So now at the number 0 to 9, if I want to shift, take the next component, I want to have basically the 1 at the beginning. And you see that if I roll of +1, actually is pushing forward, not pulling. So it's kind of counterintuitive, but the plus is pushing, the minus is pulling. So what we want to do is -1 because we want to pull everything back. Okay. So
Thanks.
We can do the difference. Yeah. Okay. So this was another example, but it's always good to search on Google, etc., how to do stuff with NumPy, because you can basically do everything, and you should never end up doing things in Python. Okay, because there is a difference in performance. It's huge. So never do for loops on data. It's not needed. Okay. Okay, final point of this presentation. that just it's a good knowledge. What if you don't have any other way than writing a for loop? What is your, how can you do it? Do you need to end up to Python? The answer is no. Your solution is Numba. Numba is this other package that is basically a just-in-time compiler for Python and compiles Python code and produces code that performs as fast as machine code. Just-in-time means that it does it, you don't have to do anything overhead, but it's ahead of time, but it's done just in time at the moment you want to execute it. It's very, very simple to use it. We are going to see it now as an example. And it produces C performance. Why did I say that the answer was ni? Because the issue you have with Numba is that you need to write Python code. So to do actually what I told you to don't do so far, you write your function, but then you ask Numba to GTify it, and Numba will compile this thing with a C, to translate this in C code and compile it. But for this reason, it's very powerful, just you need to write explicitly the for loop. So you need to know, like I did before, how to write, for instance, your operation in a for loop manner, okay? So what, let's do it now, and we can see again this example. So we saw this is how I was writing the for loop in Python. The same code, I take it, put it in a function, like I do here, okay? And I say to Numba, and I decorate it with this decorator that is ngit, that is the Numba JIT, and this one is going to be compiled. In the same way, I can produce parallel code by just saying this function should be parallel, should be run in parallel, and instead of a simple range, I put a p range, and this is going to do what I mentioned this morning, a parallel loop over the data. You need to be careful about this because the data, you need to be careful about what is known as race condition. You will see more with Yannis. But because if you multiple thread try to write the same piece of data, you run into problems because everybody trying to do the same thing. But here, this is a simple loop that you can parallelize, and so you can just do these things. So you write the loop in Python, Numba, it's very simple. You say just to GTify it, and we'll compile it for you. You don't have to do anything else. Okay, now let's have a look at the various differences. So final look about performance. So let's first take the standard code. Let me create also a function for this. So basically, it's the I copy this one without the JIT, and I name it py. So now we are going to have 4 functions where basically we want to time them. Let's for now run slower, and let's time the difference done with the first one is NumPy, the second one is Python, the third one is Numba, and the fourth one is Numba parallel, like I did here. So we can run it, time it, and get the plot that we were getting at the beginning, where we see the cost. Just a second. The difference in Python shouldn't be that fast. Okay. Anyway, this is weird at the moment. I must have something wrong in place, but okay. Basically, what we are going to see now, let's just put this one because the Python should be much slower. Okay, here I have the 3 functions that I'm running. Let's run them up to 20. And basically what you can see is that that NumPy produced code that is fast or also faster than what is done by NumPy. So this was the function defined in NumPy, taking the difference of rolling something separating the array. NumPy here, you can see that this is the NumPy. NumPy is faster than that one in both cases for the non-parallel and parallel version. And it's faster for few data as well as more. But to see better the more, I don't have to use a log scale. You can
Sorry,
see,
what's the difference between the difference NumPy and the difference NumPy parallel?
yeah, going there in a second. So so yeah, NumPy is faster. You can see here than NumPy, a bit faster, but because just is doing some more optimization. But anyway, produce code that is as fast, if not faster, than NumPy by taking Python code. So it does a very good job. It's this is non-trivial. So it takes your code here, compiles it, and then you can run it without worrying to lose performance. Okay. Here I'm showing two different plots. The one with the case where I use NumPy, the pure one, the NumPy version that is the plain one, this one on top, and then a parallel version where I'm running over this ranging parallel. Okay. What you can notice is something that maybe you wouldn't expect, that the parallel version is actually slower than the non-parallel version. This is true here online. If you run it on your local machine, it's actually faster. And the reason why it's slower is because Google Collaboratory just give us one core, one thread. And if you try to do multi-threading, Google Collaboratory actually runs slower than one thread. This is the only reason why here it's slower. That's why you see it faster. But this parallel version is basically going to run with multi-threading the loop over many components. Okay, that's the advantage of the parallel version. So it doesn't cost much to make it parallel. Just say parallel equal to, you give a p-range, and then you want to test if it's performs better than non-parallel. Okay, but this will let you run in parallel. The first one, it's always working well out. And, so concluding, if you don't have any other way around, you can still write your code in Python and very easily ask to compile it. So this is something that you should very try out. Okay, so this was the material. Now it will be good to have some questions and also kind of discussion. We see a bit now, there are just 5 minutes left. So let me conclude. So the message of this part is that if you're going to use Python, please have in mind to never do for loop on data. Always try to find another way. If your code runs slow, it's because of this, and you should never do it. There are plenty of ways to avoid it, and we saw a few of them. So either use NumPy or Numba. And yes, Python, even if it's not meant for performance, you can reach high performance by using some of these tricks. Okay. Questions?
May I ask something general?
Yeah.
If we compare Numba to a C program, will it still be slower or would it be the same?
Yeah.
How would it be?
That's a very good question. Numba is always going to be faster than NumPy, and it should reach a level of performance as a C program because it's actually getting compiled, so parts are getting optimized. Having in mind what I said at the beginning, that all of these, the statement about being faster or not than a C code, hold, or at least as fast as a C code, hold in the region where you go, your calculation costs more than the overheads of Python. a C code in this region will always run faster.
Mhm.
Also there are some overheads, but as far as you go to a region where it's you go to a region that you see the scaling of your code, then I wouldn't worry about performance at that point because it's going to be as fast as C. Okay.
Okay, thanks.
So the major issue of Python codes is that often you may introduce too many overrides that you need to try to optimize. So many packages often compile part of the codes. But indeed, if you rely on packages, you always get a very good performance. So that's one of the jobs of the packages, and that's why it's good to know what is available around to avoid to kind of reinvent the wheel while you do it. Okay. But yeah, it can be very fast. I mean, it can be as fast as C. Okay. Other questions?
Okay, I'm just thinking about a technical question that I'm using Jupyter Notebook. So is it possible to work with NumPy in Jupyter Notebook or just only Colab?
You can always use it like any other package. You import it and use it in Jupyter. There is no disadvantage of doing that. And I don't see reason why you should not do it. It's fine. You can just write in a Jupyter notebook and ask to compile it, and it's the same.
Okay.
I mean, the only disadvantage of NumPy, but it's not really a disadvantage. It's like I said, it's a just-in-time compiler. So you need to be careful that there is an extra cost. The first time you call the function, there is an extra cost. And we saw it the first time this is run. So let me reinitialize the functions. The first time you run the function, it actually runs slower, much slower than the rest. I'm going to let's see if it appears here. Because the first time you call it, it's compiling. So that takes time. You see these big peaks here. This is not because it runs slower, it's a fluctuation. This is the fact that the first time you used it here, it compiled. But then it cached the compilation and you always uses it. So what you need to be careful with NumPy, the only thing you need to be careful is that the function needs to be defined outside and never inside a function. So if I write a function that returns the function, the compiled function, suppose for instance, this every time it's a new object and gets compiled again. So it's good to know to have it the same object. That's a mistake you might need to have in mind. But once it's compiled the first time, it runs as fast as the rest. Okay, so you see, I took 1 second to compile it. It's a lot. But if you reuse it, then it's fast. Okay. Okay. Any other question? Okay, so then we finish on time, and I thank you all for the attention, and I wish you a good training guide. Okay, talk to you. Bye.
Thank you very much.
Thank you, Simone, for your presentations. Okay, so we have a short break now, and we carry on with some hands-on experience and training in 15 minutes. Thanks again, Simone.